Thank you for the introduction. Hello, everyone. This is Ruizhen Hu from Shenzhen University. Today, I'm going to introduce several works that use reinforcement learning to guide shape manipulation, especially in the case of using robotic arms. And let's first take a look at this video. Here's a robotic arm needs to grasp the object on the table and place it on the box on the left. And this work focused more on the grasping itself and didn't try to optimize the placement of the objects in the target box. And the initial states of the objects are upright oriented, which makes them easier to grasp. And the two works I'm going to introduce today can be considered to have a similar goal, but with optimization focused on different stages of the task. And the first variation is what we call as a transport and pack problem, where we simplify the objects and grippers and focus more on the packing order and final packing state. Given an initial configuration of objects, the goal is to iteratively transport and pack the boxes compactly into a target container. And the second variation is what we call as a grasp and place problem, where we don't consider the packing of the objects, but instead focus more on the grasping and placing task, which requires the robotic arm not only to grasp the object successfully, but also to place the object stably on the table in its upright orientation. One common property shared by those two problems is that although they both have very clear and quantifiable goals, there might be multiple optimal solutions for the same input. That is, the optimal solution is not unique. For example, for the first step problem, the input boxes can be packed in different ways into target container, but with the same final packing effect, as we show here in 2D for a clear illustration. And while for the second gap problem, we can see that the final state of the object still has 1 degree of freedom and can be rotated around the upright direction. When solving those two problems, we found that for this type of problem, using reinforcement learning to find a policy to guide the path to any optimal solution can get better results than using supervised learning method that tries to directly map to one optimal solution. So next, I will give more details of how to use reinforcement learning to solve those two problems. And for the first tab problem, I just mentioned that the final goal is very clear. That is to find a good packing for a set of given objects. So we first define a metric to evaluate the final packing quality, consisting of compactness, pyramidality, and stability, which I think are quite intuitive and standard for packing problems. However, unlike previous packing problems studied in computer graphics, which usually assumes that a set of shapes are given without interconstraints and focus on the packing problem itself. While in some other real-world applications, the objects are already in a physical arrangement, and the object movement must follow a partial order with access constraints. Here we use a robotic gripper to help illustrate the access constraints. In each step, we need to pick one object from the input set and then pack it into the target container. As shown in this example, object E can be successfully transported, while object A cannot, since object D blocks its way and needs to be moved first. To adjust this problem, we first encode the access constraints into a precedence graph. In more details, we allow the objects to be rotated during the transport and the packing process. So in 2D, each box will have two different states, the original state and the rotated state. And the precedence graph is used to indicate whether each of those two states is valid given current object arrangement. To construct the graph, we extract three types of edges to encode the precedence relation due to the blocking from the top or the side, including TB, LAB, and RAB edges. TB edge indicates top blocking. For example, box E blocks the top of D, so there is a TB edge pointing from E to D. LAB edge or RAB edge means the access to the left or the right side of the box is blocked for rotation. For example, box E blocks the access to the left side of B, and C blocks the right side. And here is the complete precedence graph for the input set given on the left. To pass the information stored in the precedence graph to our network for packing optimization, we need to find a way to encode all those nodes and edges. So for each box, the original and rotated state are encoded respectively. And we encode each state using its size and encode the precedence information using binary codes. For example, box A is pointed by two TB edges from E and D. So both states of A, the corresponding positions in TB encoding are set as 1. For the original state, the LAB and RAB are all set as 0, since it is only used for the rotated state, whereas the corresponding position in LAB and RAB encoding are set as 1. Therefore, the only condition for packing any state of any box is that its precedence encoding are all 0, like box B in this case. Note that the geometry information of the shape is static during the whole process, but the precedence information is dynamic, which will be updated when an object is selected and removed. For example, when box E is transported and packed, edges related will be removed, and the corresponding code will be updated. Now we have the information encoded in the precedence graph, and with a target container, our TAPNet starts to find objects for packing. In more details, TAPNet consists of an encoder, a decoder, and an attention module. The encoder encodes both the static and the dynamic information from the precedence graph. The decoder is a recurrent neural network. For each time step, it takes the object selected in the previous step and the current height map of the target container as input, and passes the accumulated information to the attention module with the encoder to compute the probability of each item valid for transport and packing. And the item with maximal probability is selected to be the output. In this example, box E in its original state is selected. The removal of box E will introduce an update of precedence graph, and packing E into the target container will lead to the update of the packing height map. So all the dynamic information gets updated. Moreover, the item coming from the same object, that's box E in the rotated state, needs to be set as invalid as well. With the information back to TabNet, the next object will be selected, which is the rotated box B in this case. The whole process iterates until all the boxes are transported and packed into the target container. Note that our TabNet only outputs the packing sequence. To find the packing position for the selected boxes, we employ a simple heuristic strategy, which tries the bottom left corner of each empty maximal space and selects one with the highest packing quality. We actually tried more sophisticated learning-based packing strategies and find that this simple packing strategy works best with our TabNet. Our hypothesis is that the heuristic packing placement strategy are more predictable, and hence it is easier for TabNet to anticipate where the next box will be placed and output the optimal box and its orientation accordingly. And to test our method, we designed two datasets. The first one is random dataset. The initial box configuration was generated randomly. And the second one is called the perfect packing solution guaranteed set. To generate the initial configuration, we first generate a perfect packed target container, what we call as candidate perfect packing solution, CPPS. Then we take the boxes out of the target container in sequence to form an initial configuration, which guarantees to be reversible for packing back into the CPPS, which means for this set, we know that the perfect packing result exists. Here we show some tab results in 2D on random dataset and a PPSG dataset. We can see that TabNet is able to find perfect packing solutions other than CPPS that are used to generate the input testing data. Note that our method can easily be extended to 3D where the whole process is the same, and we just have 6 different states for 3D shapes instead of 2 in 2D. And while for the packing quality measure in 3D case, an object is considered as stable if the projection of its center is inside the region formed by the supporting points. Here are some results on 3D cases. Each case is shown with the front view and back view of the container. Then for the second grasp and place task, we focus more on the problem of upright orientation estimation, which is a typical geometric analysis problem. There are some early works that were built based on handcrafted features, which makes them work in limited conditions and require high quality 3D shape as input. Recently, a DNN-based method has also been developed, but the network needs to be trained separately for different object categories, and the input shape is represented using voxels, which is time-consuming and storage-intensive. So to solve those problems, our goal is to design a more versatile neural network, which can estimate the upright direction of the input shape, no matter it is represented by a complete or partial point cloud, or even a single scan. And the key idea of our method is to consider it as a sequential decision-making process, where we train an agent to rotate the input shape step by step until it is upright oriented. Here, the initial and updated states of the input object can be considered as the observation, and the action is sampled from a set of predefined rotations. In more details, if we assume that the positive direction of the z-axis, shown in blue here, is the desired upright direction. Then we can add 4 rotations into the action space, including rotation around the x-axis counterclockwise or clockwise, and a rotation around the y-axis counterclockwise or clockwise. And then we can define an extra stop action that allows the agent to terminate the iteration by itself. With this action space, we can design a network to select a sequence of action to perform upright correction for a given shape. Here is the network structure of our model called upright RL. In each iteration, we extract the point cloud feature using PointNet. Then the agent will output the probability of those 5 actions. And one action is sampled and applied to the input point cloud to get the updated state. The updated point cloud will be the input of the next step, and the iteration will stop if the stop action is sampled or the maximum number of steps is reached. Then to guide the training of such a network, we need to define a reward function to evaluate the action applied in each step. So we compare the 2 point clouds before and after applying the sample action. Here we use the orange arrow to represent the current upright direction of the point cloud, and the blue arrow to represent the target upright direction when the shape is upright oriented. So intuitively, we defined a reward function to encourage the orange arrow to get closer to the blue one with smaller number of steps. And we consider the upright correction to be successful if the angle between those 2 directions is smaller than a given threshold, as in previous works. But instead of setting the threshold to be 15 degrees only, we also tested 5 and 10 degrees to evaluate the result in a more accurate manner. Then for a testing set, the success rate is used as the evaluation metric. And to collect those different type of input data for testing, we built 3 datasets from the completion 3D benchmark. And note that since we know the current upright direction of each point cloud during training, we also designed a network called BaseNet to predict such direction using supervised learning. This table shows a comparison between our upright and the BaseNet on those 3 datasets. We can see that our method generally produce more accurate results than BaseNet. The difference is more clear, especially when setting smaller threshold. For example, the success rate on the 5 degree of upright RL is more than 2 times higher than that of BaseNet for all 3 datasets. Here are some view comparison between our model and BaseNet. We can see that even for partial input with large missing part, our method can still successfully rotate it into its upright orientation. Now with upright direction obtained by our method, let's get back to the grasp and place task. Given an input lying on the table, we first take a scan to get the input point cloud. Then we use the GraspNet to get a set of candidate grasping poles and our model to get the upright direction. Here we use a gripper skeleton to represent the gripper and the orange arrow to represent the current upright direction. And our goal is to select an optimal pose to grasp and place object in its upright orientation. So we propose a grasping pose selection method based on the upright direction. The first step is projection filter, where we project the input scan and the gripper key points onto the upright direction. If some part of the gripper projection lies outside the scan projection, the gripper will collide with the table while placing the object. So we consider this kind of pose invalid. And this is a valid pose whose projection is fully inside the scan projection. These are all the valid poses left after the first projection filter step. And the second step is angle selection. We think that when the grasping pose is perpendicular to the upright direction, the contacting region will be larger and the final placement will be more stable. So we compute the angle between the grasping pose direction and the upright direction and select the one with the angle closest to 90 degrees. And with this optimal grasping pose we selected and the upright direction, now we can control the robot to grasp and place the object. Here are more demos of grasping and placing different objects. So by now, I briefly introduced the two works on shape manipulation using robotic arms and how they can be solved via reinforcement learning. Actually, similar methods can be used to solve problems in other areas. And I will give one more example in data visualization, which may seem irrelevant at first, but eventually it is also about shape manipulation in a sense. Star glyphs are a type of radio plot that show data points in a compact representation with the coordinate axis circularly arranged around a central point. And the order of the coordinate axis heavily influence its shape and thus its perception during analysis tasks. The desired shape of a star glyph depends on the visualization task. Most existing works study the coordinate ordering problem for a single star glyph with the goal to improve properties like symmetry or saliency. But for similarity search and grouping among a set of star glyphs, especially when associated to multiple class labels, the perceptual difference between glyphs becomes more important. So in this work, our goal is to maximize visual class separation by optimizing the coordinate order of the glyphs. That is, to minimize the interclass shape distances and maximize the interclass distances. So essentially, it can be considered as a reshaping problem by reordering the coordinates. And to solve this problem, we propose a reinforcement learning-based method for coordinate reordering. The network architecture is actually very similar to the one we used in the transport and pack problem, since both problems aim to find a good sequence order for a given set. So the key in this problem becomes to define a proper reward function to guide the training of this ordering network. As I mentioned, the goal is to maximize the visual class separation. So we define a shape-driven class separation measure as the reward. And the first keyword is shape-driven. which means we want to define a perceptual distance measure between two stacked glyphs based on their shapes. And a natural choice is the classical shape context descriptor. In more details, given a stacked glyph represented by a 2D polygon with first sample points on its boundary. And then for each sampled point, we create a grid and compute the relative position of the other point by counting the numbers of points falling in each bin of the grid. Then for each sampled point, we can, after the counting, we can create a spatial histogram, which is the shape context descriptor of the central point, and it can be stored as a two-dimensional matrix. To measure the distance between two shape context descriptors of 2 points, we employ chi-square test between the two histograms. And for two stacked glyphs, their perceptual distance is defined as the average distance of all pairs of shape context descriptors of the corresponding points. Note that the sample points are naturally in correspondence along the boundary, following the coordinate order. With the shape distance of each pair of stacked glyphs, we measure the class separation of the entire set by silhouette coefficient, which is also a very common measurement in clustering problem. It first measures how similar a shape is to its own cluster compared to other clusters, and then takes the maximal value over all cluster means as the final silhouette coefficient. And high silhouette coefficient indicate better class separations. We conduct a user study to justify our class separation measure. In this study, users are shown with a set of stacked glyphs without labeling. Then they are asked to manually group the glyphs into clusters. Note that the size of each cluster can be different, and the number of clusters is also decided by the users. So the average grouping quality of the result will indicate the perceptual class separation of the stacked glyph sets. For the study, we randomly synthesized 10 datasets with various dimensions, class numbers, and sizes. For each set, we find coordinate ordering with low silhouette coefficient and high silhouette coefficient. SC here is short for silhouette coefficient. And in addition, we add one more ordering following another strategy to present salient shapes with spikes for comparison. And here is the result from 20 users for those three orderings. The grouping quality is measured by comparing the user groupings and the ground truth groupings of those data. We can see that the ordering with high SC help user achieve higher grouping quality, which means that the class separation measure we proposed is useful and stable. In most situations, users were able to tell the perceptual difference between different glyphs more clearly for set ordered with a high SC. Here are some view results. We can see that the glyphs with optimized coordinate orders have better contrast between classes. And actually, the proposed method can also be generalized to other type of plots, like RadViz, where which arrange each dimension around a circle and plot high dimensional points inside the circle. Different coordinate ordering can also lead to different perceptions for RadViz. And just like stack glyphs, we also want to optimize the coordinate order for RadViz for better separation between classes. So we can reuse our network, but with the reward function replaced by the class separation measure commonly used for RadViz. And here are some view examples. We can see that the clusters are distributed further away in the optimized coordinate order than before. So to conclude, today I introduced two shape manipulation tasks and show how they can be solved using reinforcement learning. And then I show that the proposed method can also be used to optimize the coordinate order for a set of stack glyphs with shape-driven class separation measure utilizing shape context descriptors and the silhouette coefficients. And I believe that the key is to formulate the problem in the right way. That is the way to encode the observation, the way to construct the action space, and the way to design the reward function. Due to the time limits, there are many technical details I haven't explained in depth and limitations and directions for future works that I haven't discussed. But other papers can be found at my homepage. Please feel free to contact me if you find any of those work interesting and would like to discuss more. I'm ready to take any questions. Thank you.
Thank you very much, Ruizhen Fu. It was a wonderful talk. So yeah, there is about 10 minutes for Q&A session. So if you have question, please post it on the chat. Let me start one. So in your all research presented today, the network is based on sequence and using the attention network.
Yeah.
So why? What's the reason you choose this kind of architecture, especially for shape manipulation? Do you think it's such an architecture have a lot of advantage over the, like simple encoder-decoder network?
Yeah, it's a very good question. Actually, when we try to formulate the problem, it's a combinatorial problem, and it's even an anti-hard problem to solve. And we didn't find a very good solver. And then we start to explore previous works, like to see if there is any learning-based method can be used to solve that kind of problem. And we found one paper that was published on, I think it's NIPS 2018, which is, the setting is very similar to our problem, and the reinforcement learning network. The network architecture is very similar to the one I presented here, used to solve that kind of problem. And the main advantage of this of using this kind of network architecture is that it can efficiently solve those kind of combinatorial problem with very simple network component like this. The encoder decoder, actually the network architecture itself is not very complex, but when combine them together, it gets very good result for solving such kind of combinatorial problems.
I see. So the sequence can handle such kind of complicated combinatorial problem.
Yes.
Okay, so I take the question from Min Hyun Sung. So thank you very much for great talk. So he is asking that instead of reinforcement learning for the upright orientation, estimation, instead of reinforcement learning, can you use a simple regression network for the upright orientation estimation?
Yeah. This is the basenet. I think what he or she mentioned is this kind of basenet. So because for each point cloud, we do know the ground truth upright direction, and we can use supervised learning method to do the regression directly. And from the experiment, as I show here, we found that use reinforcement learning can always get better result. I think especially for those partial dataset and single scans. I think one possibility is that the shape have too many variations, especially when there are large missing parts, then the simple supervised regression cannot really handle all those weird cases. But for reinforcement learning, it rotates the shape step by step, and somehow it finds a way to the better solution of the upright direction. Yeah.
Actually, he means that iterates the regression progress multiple time in one step.
I see. Okay, I see. Okay, then the question the problem will be during the testing. You don't know how to stop, when to stop for the supervised method. For the reinforcement learning, we add the stop actions. We added the stop action, so we can know once we sample the stop action, I will just stop. This is the final upright direction we got. But for the supervised method, during the testing, you don't know when to stop. Sometimes, for example, you might already get a good result, but then you apply the supervised network again, it will derive away to the ground truth direction. I think it would be the problem.
I see. Thank you. Yeah. Is there another question from the audience? Yes, please, Takeo, go ahead.
Yeah, so I found your class transfer is very interesting, and I want to know a little bit more. So you predict upright orientation, right? And in the reward function, is in the training, ground truth is given?
Yeah, during the training, we used the ground truth.
Oh, I see. Okay. And then another question is, yeah, I'm impressed by the result. Your reinforcement learning result is much better than BaseNet, right? Directly feeding data. And my question is, when does this happen to many other questions? Replacing just simple network with reinforcement learning is always beneficial, or when reinforcement learning is better and when is direct regression is better? Do you have any suggestion in general?
Yeah, I think from my experience, I think maybe there's one slide here in the beginning. Yeah, I think for those problems, if you have very clear goal, you know what's bad, what's better, what's worse, but you don't you do not find a good way to construct the optimal solutions, or there are cases that there are multiple optimal solutions. So for the supervised learning, you have to choose one, right? You have to set the mapping from one input to one output. But when you have multiple optimal solutions, which one do you select? That would be a question. But when you know the way how to evaluate, how to measure whether a solution is a good or not, then you can use reinforcement learning to train a policy to find maybe the shortest path to any good solution. I think this is, yeah, what I can see from my experience. When you have multiple solutions, or when you cannot really construct a set of good solutions, then maybe you using reinforcement learning with a good reinforcement, good reward function to guide the training will get better results.
Yeah, so thank you very much. But upright orientation, I think, is single ground truth, right? Not multiple.
Yeah.
So I'm
so
confused.
that one it has a single how to say that? It has a single ground truth upright direction, but when you rotate the given input to the final position, the procedure is not unique. Like you can rotate the shape around the upright direction in multiple with any kind of rotations. You can rotate around the upright direction. So the whole process grasp and place the object, it's not unique. So in this way, yeah. So in this way, it kind of, yeah, using the reinforcement learning to find a path to that.
Yeah, thank you. I will try reinforcement learning more in the future. Thank you.
I have one quick question. So yeah, it's impressive that you use reinforcement learning for learning policy for the first project you presented for the packing. I'm curious how much it's generalized, for example, into different problem setting. For example, if the box size is different, then the network try to apply the same policy, but how much it's generalized, how much it performs good. For example, the container is different, for example, or box is different.
That's a very good question. Actually, in our paper, we test all those kind of different settings. I think the box size is not a big issue, because when you see the box I show here, like you have very tiny box here and very big box here. So the box size won't be a big issue, and since it's a static encoding in our input, but the number of boxes become an issue, because for the input, for the network, for most of those networks, it takes a fixed size of input. So initially, we always assume like we have 10 boxes, we have 20 boxes. And once we change the network for 10 boxes, it can only used for 10 boxes. But I think this makes the network cannot generalize well. So we have two ways to improve the, make it more general. Let me find the slides here. So one way is what we call a rolling scheme here. So when we have a larger instance, here, when we have larger instance, we, for example, here the network is trained on 4 boxes, but test on 6 boxes. So because we have encode the access constraints into the precedence graph, so we can always know which box is invalid currently. So in this case, we can choose the 4 most likely 4 boxes most likely to transpose and pack to give it to the network first, and then we pack the object. Once this object is removed, we can add 1 more object into our network, and then this the process goes iterates until all the boxes are packed. So this is one way how to deal with a larger instance with more numbers of objects than the ones we trained. And another way is to modify our encoder. So previously, our encoder is a CNN network, CNN. So it takes fixed number of input, fixed size of input. But later, we also tried here, if you can see here, these are convolution. So these are CNN. The input size is fixed. Later, we changed this CNN, use recurrent neural network. So once we use recurrent neural network, the input size can change. So then it can take more different size of the input. But once we after we do all those experiments, the difference cannot be too much. Like if our network is trained on like input with 10 boxes, we can deal with maybe 20 boxes, but it may not generalize well to 100 boxes.
I see.
So I think it
using the
has some
sequence is the
degree
key.
of generalization. Yeah.
I see. Yeah. Thank you very much. So we have reached today's time limit. So we have to conclude this session. Thank you very much for excellent talk for both Takeo Igarashi and Ruizhen Fu. We'd like to thank the speaker. Yeah. Thank you very much.
Bye.
Thank you.
the
Bye.
organizers. Thank you. Bye.
Bye.
Thank you.
Okay. Thank you.
Okay. So yeah, live streaming.
Yes, I'm leaving.
Thank you very much, Takeo.
Thank you.
Yeah. Thank you. Thank you very much. So may I leave?